run through real quick. We just went over the net area idea, that while area is always positive, the integral will see area under the x-axis as negative. And it makes a lot of sense when you're talking about displacement with a velocity graph, because a positive velocity means you move in the positive direction, a negative velocity means you move in the negative direction, and you get displacement out of that. I forgot to record, so that was my quick redo. And then the quick redo here, you will be solving integrals for functions that are continuous with a possible jump discontinuity. All right. Now, examples. You're going to find these integrals by looking at the area. So this integrand, you may not recognize it, but what I want all of you to do is write down y equals that function. Then play with that. Play with the algebra on that and tell me if you realize what shape it is. And when I say play with it, I mean play with it. I'm assuming that you saw the square root and thought, and I want somebody to see it before I get there. Circle. If I add this x squared to the other side, I have x squared plus y squared equals 1, which is a circle with radius 1 centered at the origin. However, go back to this function and realize that to see the whole circle, I had to square both sides of my equation. Right. It's a semicircle, and it's the positive square root without the negative square root. So it's the top half. And the radius is 1. Then take a look at your A and your B and draw vertical lines at those x coordinates. And then continue to draw vertical lines from the graph to the x-axis, and you'll see the region whose area you're trying to find. And what do you get for that area? I'm looking in chat. So if we were to do the area of the whole circle, we would get pi r squared. There you go. 1/4 pi r squared, which would be pi over 4. And it's above the x-axis, so it's positive. Now, for part B, you're going to take the integrand, set it equal to y, and graph that function. Everybody's graphing. You know what? I can draw a line. Oh, how is it that I do that here? I can move it or erase it and try again. Anyway, you guys have drawn this, correct? Now look at the fact that it is from 0 to 3. And draw vertical lines at 0 and 3. And then draw vertical lines from the function to the x-axis. And by doing that, you will shade the regions that you're looking at area. This little bit is under the x-axis, so whatever its area is, the integral is going to take negative its area. So a 1 by 1 triangle, what is the area of a 1 by 1 triangle? 1/2. So negative 1/2 kicks this off. And then I have a 2 by 2 triangle with positive area. And what would that give me? An area of 2. So 3/2 is the answer to that definite integral. And you need to be aware that any time you have a definite integral and you have the ability to find the area between the curve and the x-axis, you can solve the definite integral that way anytime you want. All right, I have another example for you. And this is the homework problem I didn't give you so that we could do it together, and then you have another one similar to it. This is something that I would expect to see on the AP test. So this is saying to integrate from 0 to 2 this g of x function. So I'm going to draw some vertical lines at 0, and then 2 is right here. So it actually just wants the area of a triangle that's above the x-axis. And that is a 2 by 4 triangle, so the area is 4. The next one wants me to find the integral of that same graph, but from 2 to 6. So here's 2, here's 6, and I want to draw vertical lines from the graph to the x-axis to see the region whose area I'm finding, and also to notice that it's under the x-axis. So I'm going to get negative the area of that semicircle. This semicircle has a radius of 2. So pi r squared, but divided by 2 will give me 2 pi. But because it's under the x-axis, the integral will say negative 2 pi. And then lastly, we have the integral from 0 to 7 of that same function. Now, you want to take what you've already found so far. You have already found the integral from 0 to 2 and the integral from 2 to 6. So this is going to be a positive 4 minus 2 pi. And in addition to that, from 6 to 7, draw little vertical lines and see that it's plus an area of 1/2. Good. And that is the answer to the integral. You can leave your answer this way. And if this was free response, I would recommend you leave it there and just don't even add the 4 and the half together. I don't care how easy it is, just don't. It's tempting. Okay, so that is using area to solve a definite integral. And again, you can do that anytime that you're able to use area. All right, I am now moving And we have some important properties. It isn't set on a definite integral that the number you put on the bottom has to be smaller than the number you put on the top. It is not set that has to be. But there is a formula that has to be dealt with. If you are using the formula properly, if these are in the wrong order, you actually are having a negative width. So, for example, if I gave you the integral from, let's say, 2 to negative 1 of some function, if that function is above the x-axis, then I'm dealing with a negative width and a positive height. If this integrand function is under the x-axis, then I'm dealing with a negative width and a negative height, and I'm going to wind up with positive again. But if this bugs you, which it does a lot of people when they have done definite integrals for a little bit, you can negate that integral and swap them, and it's going to give you exactly the same thing as them being in the wrong order. So it's a rule that applies to any time you feel like swapping your limits, upper and lower limits, negate the integral and you can swap them. Also keep in mind that if they're in the quote wrong order, that's causing you to have a negative width. And if you have too much difficulty, if like dyslexia starts getting the better of you, then you can put them in the proper order and negate. This is a side note, but I forgot what the stretched out. Oh, yeah, the stretched out S is the integral symbol itself. And I was joking around with first period today, and I said, so it doesn't correct. It's no longer looked at as an S. It is now the symbol for integration. Now, here's my joke. If you don't have a Halloween costume, you can grab a couple sticky notes. You can stick a B on your forehead and an A on your feet and say, I'm a definite integral. And we could go further. You could put A on top and B on the bottom and say, I'm very negative. Yeah, okay, not funny. If you look at the next one, if those numbers are telling us the x interval that we will be finding area from, does it make sense that if you integrate from A to A, you have no area? So that means if you wanted to, you could put an A on your forehead and an A on your feet and say, I am nothing. That's what I am for Halloween. But that sounds so sad. So be a positive integral. Either that, or you could have them swapped orders, but with a function that's under the x-axis. So you can say, I made my negative into a positive, so I'm positive now. I don't know. Anyway, there you go. 2 properties of integration. Now, these properties are pretty similar to some of the summation properties we looked at yesterday. For number 1, It makes a lot of sense if you look at the picture. If your integrand is a constant, that's creating a horizontal line at that C. That would also give you the height of a rectangle, where B minus A is giving you the width of that rectangle. So you have height times width. And even if they're negative, if C is a negative constant, this will turn out negative. If B happens to be a number that is smaller than A, then it will come out as negative automatically. We've talked about this one before, but again, you can add the functions inside the integral and then integrate, or you can integrate them separately. And the same with subtraction. And then we've also seen the constant multiple rule. But realize that you can actually view these rules from a viewpoint of area instead of the antiderivative viewpoint. So if you have some function, right now I'm going to talk about number 3. If you have some f of x function, from A to B, what do you do to the graph when you multiply by C? Do you remember what that does to a graph when you multiply it by a constant? Right? Stretches it. And it stretches it by a multiple of C. So if you think about all the rectangles that you might have used to approximate f of x with, every one of those rectangles is multiplied by C. And that will cause all of those areas to multiply by C if one of the dimensions is multiplied by C. And then there's a picture for the addition one that I want to grab for you real quick. If I can find where I put that. Give me 1 second. There are a lot of pages in this book. There it is. This picture would be a lot better to look at than any drawing that I'm going to try to make right now. So what this is showing is function f looks like this. Function g is this. If I add these two graphs together, I wind up getting this if I add them together. So this is f plus g. Now, if I first add them and then integrate, then I am getting this area. I'm going to erase that so that I can redraw. If instead I find the integral of f of x, I'm trying to draw quickly, and then I find the integral of g of x, and I add those together, this section is counted twice, which would account for this extra bit up here. So it's a way of showing you graphically what we saw through the antiderivative, just to reinforce those rules. Now, one more, and this is a good one. If I take the same function and I find the integral from a to c, and then I find the integral from c to b, if I add those two areas, should I get the same area as taking the whole thing at once from a to b? Now, here's the funny thing. The order of A, B, and C on the number line don't matter. This still works. Are you ready to see that this formula works regardless of order? I'm going to switch just the B and the C. And let's look at what this integral is saying. This time, the integral from A to C is the one that goes all the way down and finds the entire area. The integral from C to B, if I have it in this order, that's the reverse order. I have a negative width. So I'm actually getting the opposite sign of the area that I was supposed to get here. So essentially, I'm subtracting that to wind back at the area that I got between A and B. And you can do this for any rearrangement of A, B, and C, but I don't think we want to spend our time looking at all the different ways that they can arrange and that it works, but it's fun to take a look at. So this is a very important rule. And then, did you get enough time to write that down? Okay. Then we have those properties we just looked at. They are irrelevant to who's bigger, A or B. But these next three properties, it matters. So they have these, including the issue of A being less than or equal to B. And they make a lot of sense if you look at them. The number 6, the first one says, basically, if your graph is above the x-axis and your A and your B are going in the proper order, you should expect a positive answer. You would only get equal to 0 if f of x was equal to 0. For number 7, if one of the functions is larger than the other and you integrate in the proper order, does it make sense that its integral will also be larger? Even if they are negative. So I'm going to draw some functions under the x-axis. This is going to be f, and g always gets green because green starts with g. So if f of x is to be greater than or equal to g, then g has to be under it somehow. Now, if I integrate from x equals a to x equals b of f of x, I will get a negative number, right? If I integrate g, I will get a more negative number. And a more negative number actually means smaller. So basically, if you have one function that is vertically above the other one, its integral has to be larger, as long as you're going in the proper A to B order. And then the last one has a nice picture with it. For the last one, what this is saying is m is the absolute minimum of f of x over the interval a to b, the absolute minimum. If you take that absolute minimum's value and you multiply it by the length of the interval, you will get a rectangle whose area is less than what you're getting from that definite integral. That should make sense. And you realize that the area of the integral is everything under this pink line, all the way down to the x-axis. And then capital M is the absolute maximum value on that interval. What if? Yeah, it could be on the A or the B. And there's an equal to sign here. So there's a possibility to get equal to if your f of x function is a horizontal line. But if it's not a horizontal line and you take the absolute maximum over that interval, then the area under the curve is going to be less than the area of the big rectangle. So these are properties you can use at any time. And that is actually it. That's all I needed to go over with you, and then your homework won't be too bad either. Which would be great. Well, maybe you have some fun Halloween plans, yes? Yeah? All right, so you can have some fun this weekend. Your homework is pretty light. And then let's see. In period 1, they did ask to see one of the problems from yesterday's homework. So if you would like, I can go over that. Would you like to see a homework problem? Or do you just want to start the quiz early so you can get to homecoming?